Well, hello, Calculus 3 students. We are getting ready to begin section 12.2. We're going to be talking about vectors in 3 dimensions. We're going to look at an XYZ plane. It's very difficult to try to visualize this XYZ plane because we are trying to do this on a 2-dimensional surface. So we're going to have to imagine this point extended out in space coming towards us. So it's coming towards us 2 units, to the right 3, and up 4. So you might say, if I were to look at this as a box, it would look something like this. And I'm to imagine this point happening out in space up here. Notice you're going to use this right hand rule. This is what we're going to use. We're going to say up is positive z, down is negative z. Notice it's coming down from here. Let's plot the point 3. So let's just make some ticks. There's 3. We're going to go, they all are in the form x, y, z. So the y will be going 1, 2, 3, 4, and then we're going to go up 5. 1, 2, 3, 4, 5. So it'll be 3, 4, and then we're going to imagine that it is extended up in space to this point straight up 5 units. So I would count off 1, 2, 3, 4, 5 units. That would give this box right here. Goes up 5 units, and then all the time you're going to have to just visualize this point out here in space. So let's do the next one, which is -2. Alright, so I'm going to go -2 in the x direction, and then down 3, 1, 2, 3, and then down 3, sorry about that, -3 in the x, and then to the left, 2, 3, to the left, and then we're just going to go up 5. So I'm sitting here right now, but I need to go up 5. So going up 1, 2, 3, 4, 5. Point would be out in here somewhere, so that if I were to extend this box, I could make this box, and it would look like, here would be the top of the box, come out this direction. And I'm telling you, this can be a mess, and you really have to try to visualize what's going on here. So here's my point, the -2, and then here's my point, 3, 4, 5. Also, we can note that we have planes if we're just talking about just an XY plane or a Y. So the XY plane would be this blue one, the YZ plane would be the gray one, and the XZ plane is that pink one, looking at these as in terms of planes. Alright, this is just having us just look at these different planes where you can see the 0, 0, 3 plane. That would be, I'm looking at that in terms of the Z point, and then you can look at that in terms of the X and Y, or the Y and Z. Let's just do one. So let's look at this point 2. So I go in the X direction 2, then I go in the Y direction -3. So conveniently I have these little marks on there. So there it is so far. Now I need to go up 7. So far in this, I've got this box right in here, and now I'm going to try to go up 7. So that's one edge of the box, 1, 2, 3, 4, 5, 6, 7. There's another edge of the box there. I need to go up 7, so that's 1, 2, 3, 4, 6, 7, another edge of the box here, so I'll just go straight down. And then this one also goes up 7 till it hits right in here. This is why graphing in 3 dimensions is difficult on a 2-dimensional surface. But here's my point right there. That's the point 2, -3, 7. So if you'll envision that point out in space, then I need the XZ plane. So XZ, so X goes this way, back and forth, and it goes straight up and down. So the XZ plane would be this plane that is on the back side of this box. So let me just do it. Oops. Back side of this box as it comes out from behind it. So it would be like if you took this box and you put it up against a wall, that XZ would be the wall that we're talking about. So there's the plane parallel to that XZ wall. Stunning, I know. And looking at the distance formula, if you have an XYZ point and you need to know that distance formula, you just extend it throughout those points. It's just the difference in each squared. Take the square root. Midpoint formula is still just another extension. We'll be specifically using these equations in our next example. Recall back from your college algebra the center of a circle, spheres or balls. Now balls, if this is our center of our, if this is our sphere, then a ball would just be, it has some maximum radius, and it would mean that I'm taking everything that is contained inside and calling it that ball. Alright, I'm looking at 2 points, and let's just place them on this ball that we have here, and I'm just going to make it work. And nothing's marked here as far as units, so we're just going to make it. So if my point is 1 and then it goes -2 and then up 5, we're just going to say that point is right about here. So we're going to say this is P on our ball. Q is, it goes out 3, goes 4 this way, and then goes down 6. So we're just going to say it's somewhere along here. And we're also going to state, this is Q, that if you drew a line through PQ, they don't just happen to be 2 random points on the sphere, they happen to be a diameter. So I'd like to know the center of that sphere if this is a diameter that goes through that sphere. So the middle of that sphere, I'm just going to use the midpoint formula. So let's find the midpoint. And I'm just going to plug into that formula there and get my midpoint. I'm just going to take the 2 x's and divide them by 2, 2 y's, divide them by 2. Alright, I found the middle of that sphere. Now I need to know how long that diameter is so that I can eventually get the radius. Notice I need the center. A, B, and C is the center. I'm just going to be plopping those numbers in. Then I'm going to need the radius, and I'll be able to get that too. Let me just go get the distance of that diameter. I'm going to go get the length of it. Okay, just plopping those numbers in, I get the square root of 161. Next thing I'm going to do in order to get the equation of that sphere is I have all of the pieces. I'm just going to plug them all into this equation for sphere. Plopping those in, this is what I get. Square root of 161 squared is 161, and I'm there. Just because we've extended this to 3 dimensions and made a sphere doesn't mean we can't use the same exact procedure that we used in college algebra. And what we did there was we collected our x's, collected our y's, and collected our z's. The next thing that we needed to do was to complete the square for each one of these. So I will do that. It is a college algebra topic. If you need help completing the square, I'll go over that in the Collaborate, or you can just look that up in the college algebra. I'll have the algebra written down here. Alright, what I'm doing is just looking to see what would make this a perfect square, and you half that middle term. It's always nice when that middle term is an even number. That would be an x plus 3 quantity squared. And then whatever I did on the left hand side I needed to do on the right hand side, so that's why you'll see me in those different colors adding those up. And this would be a 25. And that means I have a sphere centered at, so I'm going to write sphere centered at 1, -3, 4 with radius 5. Just extending what we did in college algebra. We're just extending our vector information now into 3 space. Everything just extends. I'm going to attempt to draw this vector 2 and then -4 would go to the left, 1, 2, 3, 4, and then it goes up 1. So there's that vector u in 3 space. I need 2u. That just means that 2u would then be 4, -8, 2. I can just extend this out even further, double the length, and that should be going in the x direction 4, going in the y direction -8, and then going up 2 instead of just 1. -2v. -2v would be equal to -6, 0, 2. So in the x direction I'm going to go -6, so there's 5, 6. I'm not going to go left or right, but I'm just going to go up 2. Then I will draw that vector from the origin, and there is -2v. Ooh, okay, u plus 2v. That is going to be u plus 2v. U is 2, and then 2 times v. I'll get that down algebra wise. Okay, I'll just plot this point. So that's 5, 6, 7, 8, and then -4 would be to here, and then -1 would go down 1 in space, and then I would draw this back to the origin, and there's that vector. And yes, you are still supposed to imagine this in a box, but I didn't draw that this time. It's such a mess, but imagine it. Now we're going to extend our unit vector terminology to 3 dimensions. So I need to express PQ in terms of I, J, and K. So let me first get what they are. So PQ, that means that they're going to look like the x2. So I need the Q point, because that's the Q. That's the x2. -7 minus 5, so that's -12. 8 minus 3 is 5. And then 1 minus 1 is 0. Extending that to I, J, and K, that would be -12 I hat plus 5 J hat plus 0 K hat, or you could have just left that off. Find the magnitude of PQ. I'm just going to do that algebra real quick. Just plopping that in, extending that formula. The magnitude is 13. Position vector. Now let's just find the plain old position vector. Position or unit vector. Of magnitude 10 is what we've got to do next. So to do that, I'm going to find the unit vector. The unit vector is this same vector that has a magnitude of 13, but I'm just going to say 1/13 of that. So we can write it in several different forms. This one is pretty convenient. So there's the unit vector. Now I want it to have a magnitude of 10. So that means I'm just going to take it and say 10 over 13, because this has a length of 1. Now when I multiply it by 10, it'll have a length of 10. And there we have it. Alright, we have a word problem here. Planes flying horizontally due north, so I had to get, we have to kind of come to some agreement on what is north, south, east, and west. So we're going to say that y is north and south, like it always has been when we draw it on the xy plane. It's flying horizontally due north at 300, so we're going to just say 1, 2, 3. It's flying right like this. So the very first vector, plane's flying just like this. It encounters a horizontal crosswind blowing at southeast. So it's taking this vector and blowing it. I'm going to say that that's right on a 45 and at 40 miles an hour. So that'd be a little one. I probably shouldn't have drawn it that big, but that'll do. And then also a downdraft, which is going just straight down 30 miles an hour. So that's going to be a tiny one as well. I need to come up with what is the resulting vector, and that would be this vector that goes to where this thing ends up. So let's sum this up and look at our speed vector. This is going to be 300 in the J direction. Now the crosswind that is in that southeast direction, it has a X component or an I component and a J component. Both of them, just the eastwardly would be positive, and then the southerly would be negative. So that's going to be plus 40 cosine of 45 degrees in the I hat direction minus 40 sine of 45 in that J hat direction, and then downward is going to be plus, now that would be negative 30 in that K direction. So computing this, I'll write this down. This is what that speed vector would look like, and you could put it in this other notation if you so desire. There, it looks stunning there. Now I need to get the speed and the direction. You really can't do the direction other than to say that it's kind of still going to be in that northeast direction that the resultant is going to be. In the next section we'll figure out how to do the real exact direction, but we can get that speed. We're just going to find the magnitude of that vector. Alright, so that's what I get about 275 miles an hour northeast, and this is about all you can do as far as the direction goes, and that concludes section 2. Next section we'll get into how to find the angles on that. We'll extend that to the 3 dimensions as well.